Hi, good afternoon. This is Mr. Cassidy, and I'm going to be covering your first two lessons in Chapter 9. If you'd like to have your book to follow along, you could follow along on page 665, Scatterplots. So let's start with our main question of this unit. And this is actually a unit I find really fascinating. I think it has a lot of real-life applications, and I hope you'll enjoy it. So our first main question is, how are patterns used when comparing two quantities? How do we use patterns? And you might think of two quantities like age and height as being two things that might relate. And scientists, doctors, they use patterns in age and height to be able to make predictions. I'm sure some of you guys at some point had a doctor's visit where they were like, oh, we think you're going to be, 5'8" when you grow up. And that's a prediction based on a pattern of two quantities. So we're going to be exploring this area, and we're going to learn how scientists and doctors make those kinds of predictions, which is fascinating. Let's start with the actual real-life example of a pattern that you guys have been hearing a lot about right now with the COVID-19. So take a look at this. Here I've got a scatter plot is what this is called. It means a series of data points. For the first, 30 days or so, since January 14th of this year, of 2020, with the number of cases. Now, this is not mine. A fellow teacher made this document. And I just wanted you guys to see that this is actually what people talk about when they're talking about a model. They do a model of the data, means here's the total number of people who were diagnosed with coronavirus, and they make a model of that by putting all those dots on a grid. So each day it becomes the x-axis and the number of cases becomes the y, and each of those dots corresponds with each day there's a new number of cases diagnosed. And so this shows the first 30 days in the US. And I know that, if you go down to the end of the first 30 days, you see on our data table that, the case number does not seem particularly high. You've got, just under 30 cases or so at 30 days. And so this would be the data that health officials were looking at, because this is actually pulled off CDC's website. And it's interesting, though, because they have to use that data to make predictions. Let's see if there's a way for me to... I can't annotate on this screen, but what we would want to do, and what we're learning how to do, is imagine you took a string of a spaghetti and you put this all the way across this graph. Well, you could sort of do an average or a line of best fit that would go through all these dots, that would just sort of go through the middle of the dots, be sort of a perfect average. And then you could use that to make future predictions. And there's a lot of different ways we can interpret this, but that's the way doctors and scientists probably made predictions about the coronavirus back in February and leading into March. So let's pause on this case study, and we'll come back to it in a little bit. Let's get into our lesson about how we can actually make a scatter plot and then use it to make a prediction. So from here's our standard, I'll just skip over that, where we learn today how to make a scatter plot and how to interpret data in it. So here's some quick vocab. Bivariate data. Bivariate data is just the data that we use. Let me go ahead and do this. Bivariate data means it's data with two numbers. So usually we're going to use those two numbers as an X and a Y pair. For instance, on that coronavirus chart, the X was the days and the Y was the number of cases. And so bivariate data is when you're trying to compare, and a lot of times we're comparing time with something else. Your age, for instance, with your height, or the days since January 11th and the number of coronavirus cases. A scatter plot is a graph of that data. So let's look at how to make it. First, a quick review on this. Let's say I was going to graph, and here's my graph. Here's a very simple grid. Okay, and here's 1, 2, 3, 4, 5. And I'm going to put a few dots on here and just review with you graphing. So let's say I have a dot right here, and I'll call that point A. And I'll put a dot right here, call it point B. And which of those, and I'll put a dot right here for point C. So which of those corresponds with the coordinate 5, 1? Pick A, B, or C, please. And you should have picked point C. Remember that the first value is your X value, the second is your Y value, and our X value is our left or right, and our Y is our up or down. So when we're graphing, if we were going to graph 5, 1, we'd first count to the right, 1, 2, 3, 4, 5, and then up 1 unit. So we'd go 5 to the right and up 1 to get that dot. So go ahead and think to yourself, I'm going to give you one more coordinate here. Let's say it was 3, 4. Which of these numbers is the X value of the coordinate? Now you should have picked 3. And where this graph would go is you'd go to the right 3 and up 4, and you would get a dot right about here. Let's call that point D. So we need to be solid on our graphing skills to do a scatter plot, because we're going to be graphing a bunch of dots in order to do a scatter plot. And thankfully, some of that time is saved by the computer. So let's continue on. Here's a few key other vocab words that we're going to go into. So a positive association is when the data is increasing. You see a general trend going upwards from left to right. We always read graphs from left to right. A negative association means the general data is going down, and no association means the data is sort of random. There's no obvious pattern whether it's up or down. Okay, and we'll come back to these ideas in just a second. So you could think back on the coronavirus case. So I'll put it on your screen and decide for yourself, was this showing a positive association, a negative association, or no association? Here is your type of association. Decide for yourself. Hey, you should have decided positive association. It looks like the data is going up from left to right. Great. So back to our lesson. We also have two ways of describing associations, at least for now in math. We have linear associations, which means the data is close to a straight line. It just generally appears to follow a line. It means we could put like a line of spaghetti there in the middle, and the data is going to be above and below that line, but it's going to be around a line. And what that means is the data is following this line, so we can make predictions about future data points. They won't be perfect. They're like predicting the weather. At least it gives us a prediction. We also have nonlinear data. That means data that escalates or decreases faster, maybe in a more of a curved pattern. If you see more of a curve in your data, then you have nonlinear. It's not just a straight line. Okay, we're going to be evaluating those on the upcoming scatter plots. So let's take a look at our first example. Construct a scatter plot of the number of viewers who watched new seasons of a certain television show. One main thing we always are going to do is if you have a data table, the X value is always the left side. The Y value is the right. Notice that these numbers are in millions of people, but we're going to abbreviate those just for the sake of a graph. So let's see here. Well, we always let the X be the left, the Y be the right. Usually the X is going to be our time. And here would be a scatter plot. So let's check. Let's go into now what you would want to be able to do, and I know it's tough to make this interactive in any form, is to take these points and actually turn them into coordinates. For instance, that first one would be 1, 31.7. Notice 31.7, that's not going to be precise. Graphs are visuals. They aren't necessarily the most precise tools, but we would go to 1 right and up to 31.7, which is just a hair under 32, and be able to put the dot. So what do you notice about this? First, let's answer this. What kind of an association do you see with this? Would you call this data positive, negative, or no association? You should have said negative association because it does look like as each season goes on, less and less people are watching whatever this certain TV show is. Looks like it was popular at one point with many millions of people watching it, but now it's sort of like, American Idol. It's just not quite as popular when other people are watching Stranger Things on Netflix. So we saw negative association there. Second, would you call this linear or nonlinear? Now, you might have answered either way, and no harm, no foul. If you thought this was nonlinear, I see why people make that assumption. But typically, no pattern is going to be a perfectly straight line. We're just looking for, is it close to a straight line? If I can draw a line and it looks like it pretty well goes through the data, then yes, we would call it a linear pattern. And so this would be a linear pattern set. Okay. So here we've got another scatter plot. We're going to do the same kinds of questions. First, you would just look at it and we would answer several questions based on it. So first, what do we notice? What is the relationship between cost and memory? I want you to describe to me, what do you notice as the memory goes up in gigabytes? You should have said that the cost also increases. So here we would say, as the memory increases, the cost increases. Second, we would also say that this data shows a positive association. It seems to be going up in an upward direction. Now, second, would you consider this linear or nonlinear? Here's our linear versus nonlinear again. We're just going to keep referring to those. This is a tough call because I notice it's grouped like this, and it's tough to say. Now, according to our textbook, they called it linear, that it appeared to lie along the line. Honestly, I'd be fine with either answer. Now, last, what you also always want to consider is there an outlier? Now, what is an outlier? Outlier is another vocab word. With an outlier, what you have is, let me see if I can get my pencil here. An outlier, you're going to get a dot that's like way off the mark. Maybe somebody bought 2 gigs of memory for almost $200. That would be what we call an outlier. It's just way, way off. And so we use that word outlier. So take a second. Is there anything that looks like it might be an outlier? What are the coordinates of the outlier? Yes, you may have said this one. 8, 200 would be the coordinate of that outlier. At 8 gigabytes, $200, that seems much above. Now the textbook said, no, there were no outliers, but ultimately it's sort of a personal call at this point. Eventually in IM1, you'll learn how to calculate outliers. Also, we might always discuss other patterns. One thing we might see here is just that data is clustered together. It looks like there's many different costs for each amount of memory. You might pay a lot more or a lot less. Okay, so finally, so far, here's one final problem we can look at. I'll keep this brief. Construct and interpret a scatter plot. Let's assume that you did the scatter plot. Here it is. So take a look at this. Is there a relationship between the number of students and the years? And what kind of a relationship is it? Let's review our three: positive, negative, or no association. Okay. So you should have said it appears to be a positive association. As the years increased, we also had students increasing. It seems like millions more students are going to school every single year since 1999. Next, is it a linear or a nonlinear graph? We should have said linear. This does look like it is a linear association, as we could probably draw a line. Now let's look at our last type of problem. Try to decide how many students would be enrolled in 2015. So what I'm going to do this is I'm going to first sort of put a line of spaghetti or draw just my own rough line of best fit right here, just like that. And I'm just going to make do with it as it is. What I want to do is I notice that year 0 was the year 1999. So they started the graph at 0, 1999. And what I want to know is how many people would they predict in 2015? So if that's 1999, I can number up 2000, 2001, 2002, 3, 4, 5, 6, 7, 8, 9, 10. And so if year 11 was 2010, then I could go up to 16 would be the year 2015. And that would just be 16 on my x-axis. So I'm going to go up to 16. What I want to see is I sort of just go straight up at 16 years, and I decide what's the value, how many million is the prediction on this line in 2016. So how many do you think it is? We should have said 52 million. That is our prediction here. And I think my line's a little high, so it's probably going to come in a little bit lower. But we could say maybe about 52 million. They said 51. We're close enough. This is using our data. Now, this is the same thing scientists were doing with the coronavirus, right? They were saying, we predict this many people being cases or this many deaths in a month, in a few weeks. And that's what they were doing, same as we're learning how to do here. So we could close by going back to our main question. How are patterns used comparing two quantities? Here's some sample answers. But again, it's sort of a really interesting area of math where we're actually applying what we know about lines and graphs in order to make predictions. So we're going to carry on from this. We're going to extend this a little bit to learn about a line of best fit. I have to switch the lesson to lesson 2. And get back to my presentation here. Okay, let's take a minute to recap and have you answer a few questions here about lines of best fit. So we have 3 graphs here. Would you call them positive association, negative association, or no association? Okay, on the first one, you should have said that it is a positive association. It looks like every day the temperature is getting hotter. And I'm sure you're noticing that at home as well. Here, ticket prices. Positive, negative, or no association? I would say negative association, as each ticket price, as you buy more tickets, as the ticket price increases, the number of tickets sold goes down. So you want to charge $10 a ticket, you actually end up selling maybe a few less. Last, weekly gas prices. Here's each week. And you should have said positive association. Okay, moving right on. How are patterns used? We're continuing to explore this idea. How are patterns used when comparing two quantities? Well, here's our standards. We'll jump over this. Still, one of our focuses in 8th grade, and you're going to explore this idea a lot more next year. This year, we're learning just the informal method of forming a line of best fit. So, let's get into it. So, let's just look at what we're learning here today. We're learning how to use a line of best fit to predict and then use an equation to make predictions. So, what we'll have is a scatter plot, something like this, like we learned how to do on the last one. And we'll make a line through the middle. We're going to make a perfectly linear line. We'll make an average line. And then we're going to make predictions using that line. So we call that line a line of best fit. So let's take a look at a problem. Here we have the years since 2000 and the average cost. Remember that this is going to be our X values and this is going to be our Y. And let's take a look at what this looks like. Construct a scatter plot and assess a line that best seems to fit it. So here we are. This would be an example answer. You draw this scatter plot, you put all the dots here, and then you draw the line of best fit. And we just have the main point of the problem, and part of what we have to do, and scientists have to do this too, is to assess the line. That means, do you think this line fits the data well? In this case, the answer is, yeah, it's fairly good, because what you're looking for is to fit the data well is the points should be above the line and the points should be below the line. It needs to be sort of surrounding the line so that the line is in the middle. The closer it is to the line, the better. In this case, it's pretty close. So we would say yes. Most of the points are close to the line, so the line of best fit fits well. Let's take another stab at that. So here we have, never mind. I don't like this problem. Let's move on. So how about this? We're going to use the line of best fit to make a conjecture about the cost of cookies in 2013. Now, this is the wrong graph. So I need to go back actually to our previous one. Here we are. Here were the cookies. And here was the graph of the cookies. And no, that's not the graph. Here's the graph. There's the graph. And we want to predict 2013. So I want you to look. Notice that year 0 is 2000. What number on the x-axis will be 2013? You should have said 13. 13 would be 2013 because 1 would be 2001, 2 would be 2002. So now, using just your eyeballs, go ahead and look at 2013. Go up from 13 here and try to make a prediction about what will the cost of cookies be then. Okay. So you should be going straight up right here between 12 and 14 and seeing where this line of best fit goes through right there. And so your prediction should have been about $3.35 or $3.35, right about there. All right. So next, writing a line of best fit. This is our final goal, and it does take a tiny bit of review. Let's say we have the scatter plot already done. We want to write a line of best fit, and we need to explain the y-intercept and the slope. This requires several skills that we've already covered in class, but I need to flip screens here. So let's really briefly cover the skills of writing a linear equation. Remember, we learned how to write linear equations much earlier in the year with y equals mx plus b. B stands for begin. That's the y-intercept. Y-intercept. So that's where the line intercepts the y-axis here. So let's take a look. In this case, the y-intercept is right here at the number 3. I would write y equals mx plus 3. I'm leaving it positive 3 because it's intersecting at positive 3. Why don't you go ahead and practice right now with problem 2 here. Would you try to fill in the blank for y equals mx plus blank? What number should go there? You should have come up with the number 6. Now, please don't get confused with the x-intercept. We should be looking at this number 6. All right, next, how do we fill in m? Well, m is our slope. M stands for how the line moves. Move is always a relationship of rise over run. It means how far up or down it goes and how far over it goes. To do this, you need to find 2 points on the line where it's really going through the coordinate grid as best you can. And you're going to need to do a bit of an estimate job on the actual problem in the book. So here I have 2, 4, that's where it's going through. And to find the rise and over run, now we could use a formula, but I like to just do this on the grid since this grid works. It's going up and over here. It's going up 1 and over 2. So let's fill those numbers in. Which number is the rise? You should say 1. Which number is the run? 2. So I'm going to substitute that for the letter m. Remember, x stays the letter x the whole time. So our answer should be y equals 1/2 x plus 3. That's the equation of this line. M is up 1 over 2. The whole line goes up 1 over 2. If you thought it was going up 2 and over 4, you would actually be correct. It's just simplified. 2 over 4 simplifies to 1 over 2. So here, y equals mx plus 6. Go ahead and fill in the m. Okay. You should fill in that it's going down 1 over 1, which you may remember means nice negative. And so we go, the rise is down 1, which means negative 1 over 1. And we could simplify that. So the equation of this line is y equals negative 1x plus 6. All right, let's try 2 more. I'm going to have you do the whole step. So first, fill in the b for y equals mx plus b for this problem. Y equals mx plus b here. You should have filled in negative 7 for b. Okay, what number should go for m now? We filled in 7. What number should go in for m? Pick 2 dots that really go through. All right, I'm going to pick the 2 dots, and I want you to fix your answer if you didn't already do it. So I'm going to pick this dot at the y-intercept here, and I'm going to pick this dot right here. It looks like that's it. So what's the rise over run? Fill in the fraction here. You should have gotten y equals 3 over 2x minus 7. All right, last we get more of a grid with the line of best fit that's more realistic. Here we have John's savings account, and here we have every month. What is the y equals mx plus b here? Y equals mx plus b. Start by filling in the b for begin. What do you come up with? You should have come up with 300. This savings account started at $300. Now fill in the m, the rise over run. Now notice, you might say, oh look, it's just going up 1 over 1. I know that's really tiny there. Up 1 over 1, but remember these units matter. So how much is it actually rising every month? You should fill in 100 over 1, x plus 300. Now, our final goal with the line of best fit is to interpret this. And so what we want to say is, what is the line of best fit? This is, imagine John's bank account. This is the line of best fit here. The y-intercept means he started at 300. The y-intercept is always where it starts. The M stands for move, so how much is it moving? $100 more per month on average. On average. Okay, so from there, let's get back to our lesson and see what we know. So, in our lesson, we were looking at this scatter plot. So first decide, is this a positive association, negative, or no association? You should have said positive association. Next, would you say this is linear or nonlinear? You should have said linear. Great. Let's go ahead and write an equation for the mx plus b. First, what do you think is the b for begin? You might have said something like 90. I think that's about accurate. So I would say plus 90 here. Great. Now, what do you think the m should be? Now, don't look at the dots here. What you want to do is look for points that are really close to following the axis. Here I notice this one's pretty close. And let's find another one that's pretty close. Well, this one's pretty close. Is there anything closer? Yeah, I would maybe just use this one. It looks like I went up and over. And what is the rise over run? So you should have said it is 25 over 1. So our actual line of best fit, y equals 25 over 1x plus 90, would be the equation of the line of best fit. Okay, so what does the y-intercept mean in this case? Look at what the y-intercept means. So you should say the y-intercept means that there were 90 million subscribers at the beginning of at 1999 on the line of best fit. Next, what does the slope mean? Okay, you should say that this looks like every year on average about 25 million subscribers more are added. Great. And last, what if I asked you to make a prediction at the year 2009? 2009 is what I want you to make a prediction of. Well, that would be 10 years since 1999, right? So how we would do that is we're going to actually plug in the 10 as the x value. Since years are x values, we can just put 10 for x, do 25 times 10 plus 90, and we should get a prediction for 2009's years of subscribers. So 25 times 10 is 250, plus 90 equals a total of 340 million. Now, just like the weather, just like even the coronavirus, these predictions are not necessarily accurate. They just help people make decisions. which is why we've been on shelter in place. So let's actually go back and revisit our scenario here, and you can see we're going to move on to how patterns can be used when comparing two numbers back with our actual data set of what's been happening in the United States. So this was the first 30 days, but notice the data continued from there, and it looked linear, it looked positive, it looked like it was increasing at a constant amount, which normally wouldn't be a cause for alarm. But then, when you added the next 17 days worth of data, look at what happens to our graph. Is this still linear? No, it's nonlinear. You actually see this smooth curve start to developing. And so this is what scientists were looking at, going, no, wait, this might not be a linear course of this virus, that actually people are turning out to be infected at a much more increasing rate. And so as you got to March 2nd, and that was just a week and a half right before our schools closed, we were starting to see this alarming rise that if this continues, as you start making predictions of 50 days, 100 days into the future, I can imagine being a politician or a health official or anybody looking at these numbers. The prediction means we might have a huge number of cases in a very short period of time. So that maybe helps explains why we're sheltering in place right now, and why I think they have talked so much about flattening the curve, because based on this model of the data, they're trying to change that model so that our lives are less impacted by this virus. I'm not going to get into all the politics of that, of course, but as always, I hope you're doing well. Stay safe and be well. And I thank your minds and your hearts for this extraordinarily long video, only one for the week. But I hope you guys are starting to see this is actually real life how we use math. And what scientists would want to do is find that perfect equation that really helps make predictions based on the data on an actual scatter plot. All right. Have a great math afternoon. I'll talk to you later.